Welcome to Study Loop.
In this question, we're looking at a simultaneous decay, right? Where we have two decay ongoing at the same time, starting from a primary nuclide one over here, which decays with some decay constant. Let me just call this lambda 1 to 2, and then 2 decays to 3 with some decay constant lambda 2. Now, we know that for 1, let me just call this the number of nuclides as n1 is equals to the initial number of nuclide 1, n1 naught, times exponential negative lambda 1t. Alright, so this is at any time t. Whereas for 2, it's slightly complicated, right? For 2, it has some addition of nuclides from 1 and also some loss of nuclides due to decay to 3. Right, so it's not that simple to write down n2, but rather we can only write down how n2 changes, right? The rate of change of n2. In this case, the n2 over dt at some time t is equals to the rate of decay from 1 to 2, which is increasing its numbers. So this is rate of decay. It's written as lambda 1 and 1 t. And then we have loss of nuclide as due to decay to 3, right? So that's a minus lambda 2 and 2t. So we do not know what n2t looks like yet, right? And this is the only equation that we can come up with. Right, so substituting this equation actually into here, get lambda 1 and 1 naught e negative lambda 1 t. Now this is a differential equation, and in the question we are asked to solve, and we are given a clue, right? That is to assume a trial solution, right? So we're going to assume that the solution for n2 t in general is going to be equals to n1 naught times h1, which is some unknown constant for now. Just leave it as h1 times exponential negative lambda 1t plus h2 exponential negative lambda 2t. Assuming this is the solution, we're going to substitute that into our differential equation and then try to find the relationship. On the exception where we are starting entirely from only 1, right? So at the start, we have this condition that we're going to hold n1 at time t equals to 0 goes to n1 naught, and 2 at time equals to 0 is 0, and then 3 equals 0 is 0. Right, so we only start with n1, right? This is the condition we're going to set, and we're going to try to solve for this equation. So first thing you want to do is to find what is the differentiated version of n2t, right? Assuming our trial solution, I'm going to differentiate with respect to t. So the exponential term, we just bring down the power lambda 1, and we keep same term. Alright, and then we're going to put this into the equation. Right, so we have from our previous equation, this is our differential term is equals to this entire term, which would be lambda 1 times and then we have the minus the lambda 2 and 2t. And our n2t is this equation over here. Now we see that there is a common term, which is n1 naught. And we can kind of get rid of it. Alright, and then we can try to bring the terms, right, of exponential negative lambda 1t to one side, and then we're gonna also bring all the terms with exponential lambda 2t to the same side, right? Just gather them together. All right. So for exponential lambda 1, all right, we have keeping it on the left hand side. Sorry, we'll keep it on the right hand side. So we have lambda 1 from here, and then we have minus lambda 2h1, and then we have minus h1 lambda 1, but since there's a negative over here, it becomes a positive on the right hand side. Okay, and now we bring the lambda 2 terms. So lambda 2, we have negative lambda 2h2, and then from the left hand side we have negative h2 lambda 2, which becomes positive on the right hand side. Okay, and now we know that this term basically goes to 0, right? And now we have a very nice equation, which is we can get rid of this as well. We know that T is always positive, right? Which means that this term can never be will never be 0 because it is a finite value. So we can just get rid of this. We can divide this away, right? And we are left with this equation over here. And then we want to make h1 the subject. h1 will be equals to lambda 1 divided by lambda 2 minus lambda 1. Alright, so this is the final equation that we should get. Now, of course, not forgetting our initial condition, that is n2 when t equals to 0 must be 0. This implies that from our trial equation over here, when t equals to 0, this term goes to 1, right? The exponential term goes to 1. What we're left with is just h1 plus h2 times n1 naught h2. n1 naught is non-zero, so we can divide this away from the 0. And we're left with h1 is equals to negative h2. This is the equation. So we have this, and we also have this, right? Two equations, two unknowns, h1, h2, and we can solve, right? So h2 is just negative of h1, which is lambda 1 over lambda 1 minus lambda 2. So very nice. Now we can put that back into our n2 equation. n2t is n1 naught times h1 plus h2. Okay, and that should be the final equation. And this is for a simultaneous decay, right? Where we start with only the primary nuclide at the start. Now to look at actually the last part, we are going to put in an actual nuclide, which in this case is uranium, right? So 1 becomes uranium, 2, 3, 4, and then it decays into thorium, 230, which then further decays down to radium 226. And we're going to use our solution to figure out how many samples there are, right? We know that at time equals to 0, we only have uranium 234, right, which satisfies the assumption from our previous part, right? And we have initially 30 grams of uranium 234. We want to find what is the mass of thorium 230 at T equals to 2.46% of our 5 years. First thing we want to do is to find out what is N1 naught, the initial number of uranium-234. Alright, so we take 30 grams, which is 30 times 10 to the power minus 3 kilograms. Divide this by the mass of each uranium nuclide, which is 234 U in terms of atomic mass units, and we change this to kilograms, right? So 0.66 10 to the power minus 27. All right. So this is the number of initial atoms. Next, we want to find what is our lambda 1 and lambda 2. So we know lambda 1 is basically the decay rate of uranium, which is just ln 2 over the half-life for uranium. This is 2.46 times 10 to the power 5. And then for lambda 2 is the decay rate of thorium. This is ln 2 over the half-life of thorium, which is 7.54 times 10 to the power 4. Alright, we are keeping the units in terms of years, right? Now to figure out, we have one of the more important coefficients, right, for the N2 term. Right, remember that our N2 term is like this. We want to find this, right? This was one of the key terms, which is basically lambda 1 over lambda 2 minus lambda 1. Using these values, right, we substitute that in. This should be about 0.44197. Alright, and then now we can substitute in N2 at this particular time t, where t is 2.46 times 10 to the power 5 years. Be N naught, which is 7.7205 to the power 22 N naught times, we have lambda 1 here, lambda 1 over lambda 2 minus lambda 1, and then this is just the negative version, right, of lambda 2 minus lambda 1. So this is 0.44197 times exponential negative lambda 1 over lambda 1 times t, which we know, right, lambda 1 is this, and the t is just 2.46 times 10 to the power 5, right? So this multiplied by 2.46 times 10 to the power 5, we can cancel out, we just left with ln 2. So this is actually just negative of ln 2 minus, because of this minus sign over here, minus exponential. In this case, you get on 2.46 times 10 to the power 5 divided by 7.54 times 10 to the power 4. Okay, and then putting it into the calculator, we should get 1.3506 times 10 to the power 22. And then to calculate the mass, right, the mass of thorium, multiply this number of atoms by the mass of each of this, which is 230 U times 1.66 to convert into kilograms. You should get about 5.16 times 10 power minus 3 kilograms, or just 5.16 grams.